So I wanted to quickly share my thoughts about this problem, as I think it's a good, greedy problem that involves some optimizations and observations that are good to know. So initially we are given a set of dominoes containing only numbers from 1 to 6, so no zeros, and we want to generalize one number across either the top or the bottom. So let's say, given this example, we have four twos on top and two twos on the bottom, so we just flip the bottom to the top and make 2 common across the whole row, which is top. We just did 2 rotations, or let's say flips. I think flips is more convenient, and we return to 2, which is the minimum number of flips. We could also flip the 4 on the top to make the bottom the same number, but that would need 4 flips, so we return the minimum number, which is 2. So a good observation actually for this problem is, given that we need to generalize the number on each or every one of the dominoes, so let's say 2 and 6, this 2 and 6 doesn't contain a 2, so that would make 2 not a valid number to generalize. So using this observation, we can initially consider all the numbers as a valid solutions and start looping through each one of the dominoes. So let's say we came across 2 and 5, okay? We came across 2 and 5. That would make all other numbers other than 2 and 5 not a valid solutions. Because let's say a 6, how can we make a 6 here if we don't even have it on this domino? So, and of course each domino can only contain 2 numbers, so at each step we can exclude any other number than 2 and 5. So after iterating through the first domino, we would just consider 2 and 5 as valid solutions, and when we come across the second domino, which is 1 and 2, we now can exclude 5 and we are only left with 2. So 2 is the only number that we can generalize. So let's say this 2 and 6 is, let's say, 3 and 4. That would exclude 2, making us left with no solution. So we immediately return -1, making it an early termination. Okay. So if we finish iterating through the whole dominoes and we are left with valid solutions, we would just return the minimum number of flips needed. So that would make us construct an equation making it n is the number of the dominoes, okay, minus, let's say, count tops of I. So let's say 2, we would have a count top of 4 for it, okay, and we would take the minimum between n minus count tops and n minus count bottoms as well. This is basically would be a hash map, okay? So for count tops it would be, for 2 it would have 4, and for count bottoms for 2 it would have 3. So 6, which is the number of all the dominoes, minus 4 would be 2, and 6 minus the occurrences of 2 on the bottom, which is 3, would be 3. So we take the minimum of 2 and 3 and we return it, which is 2, okay? So let's start coding. I'm going to use Python, okay? First we would have n, which is the number of dominoes, to make it easier for us to write the code. So it would be the length of tops. We are given that bottoms are the same length of tops, okay? And we would have a valid as a set. We would initially have 3 and 4 and 5, basically all the numbers. And we would have Okay, so I mentioned that this could be a hash map, but given that we only know they are only going to be 6 numbers, we can just simply use an array, okay? And I'm going to make it a length of 7 to make it one indexed, okay? I'm going to make it one indexed array to just simply make one map to 1, okay? And the same for count bottoms. It would be an array of 7, one indexed array. And after that, we just loop through each one of the dominoes. And so for this excluding the invalid solution, I'm going to use a set intersection operation. So we would find the intersection between the current valid set and another set of the current top and the current bottom, okay? So bottoms of I and tops of I. So that would make, let's say, 1, 2, 3, 4, and 5, and 6, the intersection of the first domino, which is 2 and 5. It would just output 2 and 5. Okay, we basically found the common between both the sets. And we just count the occurrences of the current top and count the bottoms of I plus 1. And for this early termination operation, we would check here if valid is empty, just return -1 to make the algorithm more efficient. After that, we would make our flips set to a maximum number, so we just make it n, okay? And we simply iterate through each one of the valid solutions, and our equation, we are going to minimize the current flips, and we get the minimum between n minus count tops of valid and n minus count bottoms of valid, and after that we just return the flips, okay? For I in range n, what did I do wrong? I just forgot that n, actually. So let's try again. Yeah, so I guess this should work. Yes, yeah, as an accepted solution. Okay, so this is O of n, and this should be considered O of 1, as we are just iterating through a maximum of 6. So that would leave us with a time complexity of O of n for this for loop, and we basically used an O of 1 space because they are just all constant spaces. That's an array of 7, an array of 7, and a set of 7. And this operation is O of 1, given that both of them are of a fixed size. We already know this is O of 1. So yeah, this is considered an efficient solution, actually. Yeah. Thank you for watching.